Hey, howdy everyone. I'm Michael Perch, and today we're going to talk about how to build a workflow for subsurface modeling. And so we'll cover the basics of workflow design. We'll get kind of mechanistic about it, mechanical about it, talk about how to put all the parts together, talk about all the various types of parts, the building blocks that we have for building our workflows. And then we'll get into some very simple discussion about data loading, and a little bit about data operations. And I will include supplemental lectures or videos in which I will go through Python code with data frames and ND arrays, in which I'll demonstrate how to do this. For the purpose of this lecture, I'll just simply show it. So if you're interested in seeing the actual hands-on section, go ahead and look a couple videos ahead from here. Okay, so let's talk about this idea of workflow construction. And so first and foremost, what you'll note is you'll go back to what we talked about in lecture one. In lecture one, we talked about the common workflow that's used for the purpose of subsurface modeling. This is kind of our, if we're talking about building reservoir models, this is a very common type of workflow that we use with very general topics or bins. And of course, if we're building a subsurface model, we'll have our own specifics of how we accomplish each one of these parts. And so we'll first start out by specifying our goals, having an inventory of our data, understanding what is available to us, and then we'll go ahead and we'll develop a conceptual model. And of course, we showed a workflow for this before. There's a lot that goes into building up that conceptual model, all the data integration challenge that we face in the subsurface, seismic, wells, analog information, expert knowledge, and so forth. There's quite a bit to put in. Then what we'll do is we'll go ahead and we'll infer the various statistical parameters that we will be working with. And these statistics are at the heart of any type of combined deterministic and stochastic or just purely statistical model. We'll want to still build estimate models, spatial estimates of the properties of interest, because as we mentioned before, it's a good opportunity to visualize the property of interest given the data that's available. There's a smoothing bias, of course, it's not the right heterogeneity, but without the heterogeneity, we're much better able to see if there's fundamental data issues, if there's a sampling issue. Often the heterogeneity may mask that. Of course, we do need heterogeneity, so we will build simulated models, realizations, and scenarios so that we're able to capture the appropriate level of variability, heterogeneity, correlation between our variables, and we'll post-process the models. We'll try to summarize them. We'll try to understand if there's some fundamental issues with the models. Maybe we need to go back and do a recycle. That always happens. That's quite common. And we'll have a transfer function and we'll end with a decision. Now, we also talked about in the previous lecture, project goals or purpose. And we talked about, there was about 9 of them. They were summarized in the book that I've written with Clayton Deutsch and from 2014. But for the purpose of the workflows that we will demonstrate in this class, let's assume that our project goals are going to be first and foremost to build a numerical model. That's the idea of having a platform that integrates all the available information together in a unified understanding of the subsurface. It's a numerical reality. Nobody can wave their hands. The whole project team has to commit to something. It's in the model. And now we can all look at it and we can debate it and we can discuss it. Much easier to do than if we leave everyone's individual and independent, perhaps, concepts unsubstantiated. They're not in a numerical reality. We're going to establish what's known and what's not known, critical risks. We can have numerical support for any future investigation, and it's a communication tool, as I mentioned. So that will be one of our purposes of modeling in this course. Also, to evaluate different recovery processes, we will look at a variety of different methods by which we can exploit the resource that's available to us in the subsurface and try to optimize based on the available information. The opportunity is also there to evaluate whether or not there's a value to additional information. What's the value of that information? To export the statistics and also, I should say, to make a decision, because we will make a decision, or maybe more than one decision in the course. We'll see how it goes. So if we're building up a workflow based on steps or fundamental building blocks, let's talk about what those building blocks could look like. And so there's a variety of different blocks that we'll be putting together. This may include loading data, taking the data from some original raw format, digital format, and getting it into a data structure that we can work with. Then once we have it in a data structure that we can work with, there'll be many different types of steps by which we format, check, clean the data. This is all about getting the data ready for our workflow. In many studies, we find that this effort around cleaning up the data, it can in fact be 80% of the effort. Now, in this course, we have provided somewhat pre-cleaned, ready to work with data, so we will not have to spend that time, but we'll still comment on this effort. Run statistical calculation, a visualization. Histograms, location maps, varograms, trends, conditional probabilities, data mining, or some other type of advanced way to interrogate your data, your models, the statistics, in order to understand what's going on with your subsurface case. You could also run an operator, some type of numerical operation. There's so many different that we could work with. Declustering, spatial continuity calculations, spatial estimation simulation, model post-processing, distribution transformations, different types of deep biasing. In addition to the declustering, there's so many things that we can do. Another step could be the transfer function. Transfer function is any summary of the model that's then used to support decision making. Could be as simple as a volumetric calculation. You build your models and you just calculate how much oil is in place. It could be very simple. Or it could be a more advanced connectivity analysis, a trend calculation, flow simulation. It could be anything. The main point is that's the chance to take the model, that spatial numerical representation, and turn it into a number that directly impacts the criteria on which we make the decision. It becomes decision criteria. Now, typically, you might wonder, well, what is that criteria? Well, it turns out that usually it's the one that relates directly to value. Everything we do, every decision we make is to maximize value of a project. The transfer function gets us into a decision criteria that relates directly to values. And that's often going to be in dollars. Now, what does it look like if you build a workflow using these elementary types of steps? What could that look like? And so we could create an example demonstration workflow that's completely generic. We're not going to fill in any of the boxes with any information. I'm not going to talk about any of the details of what's going on here, but just give you a sense of the way that we would have a flow that is going to move from data to a decision. So our first step is we would start with an input being some type of raw well information. So for this example, we're only dealing with wells. We won't specify anything about the properties. And so when we do that, we'll have an operation which is just loading the data. We're loading the data into a data structure that we can work with. And so the output is going to be that data object, that structure that we can now work with. Now we'll have a step where we'll do some cleaning of the data. And there's a variety of things we can do to clean data. And the output will be data that is effectively cleaned and it's ready to work with. Now we'll run our first calculation. That calculation results in a statistic, a statistical summary that tells us something about the behavior of that spatial phenomenon that we can use for modeling. We have an operator here. That operator could be the formation of a model. Maybe a property is being modeled. And so the output from that would be a model. Output number one is, in fact, if it's a modeling step, it would be a model. We would visualize and check that output, and so now we have QC'd output. But maybe we need to work our modeling workflow is not that simple. We need to have multiple steps of modeling, multiple steps of different types of operators. And so we have another operator. we're taking that QC'd output number 1 and using it as input into that operator, and the output for that is a new output, number 2. We visualize and check output number 2, and the result is now we have QC'd output number 2. So we have 1 and 2. The QC'd, we're comfortable with them. Now we apply QC'd output number 2 to the transfer function. The result from that is decision criteria. It is something that relates directly to value. And from that, we're now able to make a decision. Do we go or not go with the project? How many wells do we drill? Do we gather more seismic? Whatever the question might be, we have a decision related to that question supported by all of these steps that were our subsurface modeling workflow. So let's talk a little bit more about a workflow. And so what is a workflow? Well, we can step back and say that it is the data, the statistics, the models flowing, evolving, updating, developing from step to step. We're moving towards that final goal to support a decision. The well data in a data table, the seismic data and other mapped data or information or concepts along with models, which are again going to be gridded, are passed from step to step. The complete subsurface modeling workflow is commonly going to be pretty complicated. There's going to be many steps that are interrelated to each other. Also, the process is often sequence dependent. You need to first do data cleaning and transformations before you can do varogram calculations. And so there's going to be, we can't just willy-nilly go in any order. We're going to have to move in a sequence of dependent steps. Visualization and checking steps are required probably with every major significant operation. You're going to have to check to make sure that there's not some type of error that creeps in, otherwise it will taint the remainder of your workflow. And so let's take that example generic workflow and let's put a little more specifics on it now. Let's say that we're working with a GeoEAS well data file, which would be the standard file format used within GeoSlide, which is commonly known open source software in geostatistics. We're going to want to load the well data from the GeoEAS format to a Python data frame. The data frame is very convenient. It's available to us from the pandas package within Python, and it allows us to do a lot of really efficient manipulation, checking, and so forth of our data. It's very nice. So we can rename our variables. Maybe they came in with names that are very awkward to work with. Maybe we want to simplify or be more consistent with our naming conventions. We may remove missing values. Maybe we're going to do something to impute them or to fix or to correct. Or maybe we want to truncate and remove negative values. We know the negative values are erroneous, or maybe they're indicative of very small values, and so we'll use some type of minimum value for truncation. The result of that and other types of data cleaning steps is going to be a clean data frame. We're comfortable working with this for modeling. Now we still have issues with bias, and so maybe we want to conduct an operator, a calculation of declustering, and we'll calculate the declustering weights. So now the output from that is we have declustered, cleaned data frame. We have weights available to us to account for the spatial bias in sampling. Want to visualize and check this now. Look at location plots, make sure it all makes sense. Look at location plots of the declustering weights, make sure that they're fine. Check the locations at which we have treated missing values, make sure they're consistent. There's so much we can check. So now we have QC'd, declustered, clean data frame to work with. Maybe we require Gaussian transformation because our workflow includes steps or operations where we're doing Gaussian-based simulation. Our statistics need to be calculated in Gaussian. Our varogram models are based on a Gaussian transform variable. So we'll go ahead and we'll do a Gaussian transform, and now we have Gaussian transform, standard normal, with QC, declustering, cleaned, and so forth, and we would be ready for another step after that, maybe varogram calculations, then maybe Gaussian-based simulation, maybe we do some trend calculations. There's so many things that can work into or be part of this workflow. But I hope you can get a sense of just how many details, how many steps we could be involved to flow the data through statistics and models to work towards a decision. Documentation is essential. Every step includes expert decisions. This is not plug and chug. We don't just put things in and push the button and run it. We have to make decisions all the time. Now, one of the benefits of using code, of writing code to effectively script our workflow to make it repeatable, is it does provide us a very useful audit trail. That in itself is documentation. You take this workflow, if it was written all in Python, and you would be able to reproduce it yourself, even though you didn't write it. You'd be able to look at my decisions based on looking at the code and seeing what I hard-coded, what I put as an input. How did we do it? Now, we should comment that it does take probably 2 to 3 times longer to script up to provide that type of automation to the workflow. If I just opened GSLive and did these steps in GSLive, I could probably do them pretty quickly. Maybe in half the time, a third the time. I could just quickly run a workflow. Or in Patrol, I could open Patrol and just run the steps. But if I take the time to carefully script it up, to automate it, then it provides you the opportunity of having the audit trail. But also, just think about every time you've worked on a project like subsurface modeling. How many times did you get it right the very first time versus how many times did you have to redo it, change something, update, rerun it? Almost every time we have to do things over and over again. There's iteration, we learn from it, and so it's worthwhile to do some type of a scripting up of the workflow. Okay, it's essential to document the many modeling decisions, and that script is not sufficient. There's a lot of metadata, there's a lot of details around your decisions that are not captured within the code, even if you code up your workflow. You should provide metadata, information about your decisions, not directly the decisions exactly, but something in addition to that. Let me give you an example. We loaded the well data at this step, and we loaded it into Python into a data frame from Pandas. What is some of the important information? Well, who provided you with the well data? When did you receive it? What does it include? What does it not include? Maybe there's some information about the data that goes further. The porosity was from neutron density well log, calibrated to core measurements. It was set to a very low porosity value within this fraction of shale region. There's so many decisions that go into the data. These should be documented so we understand them. Maybe let's take the next step where we were doing data cleaning. Values below a certain threshold are to be considered below measurement threshold and should be set to a very low value for porosity. Fair enough, rather than taking something that's really just an erroneous measure and trying to look for patterns in it, it's below measurement tolerance. We should know that. We should know about the quality of the data coming in. Declustering, we performed declustering. We just said, okay, we did declustering. But if you're doing cell-based declustering, the cell size is essential. It's a critical part of the declustering operation. And so we can defend that here. Cell size was selected to be 200 meters isotropic, I'm assuming here squares, based on a nominal well spacing. There was some more or less even spaced wells, and then there was some infilling or something like that. I could go on and explain the remainder, but I hope you can see what I mean, that there's a lot of information that should be documented beyond simply the scripted workflow. So we have to move beyond building the scripted workflow to providing real documentation. You are writing to your future self. Have you ever remembered doing something, maybe in grad school, maybe in undergrad, and then going back 2 years later to it? Could you figure it out? I've done that many times, and I don't know what I was trying to do. That happens all the time. This documentation will allow you to actually pick it up again. You're also writing to your replacement. That's great. If you think about it on a project team in industry, most people will be moving around every 2, 3, 4 years. The project team turns over. Not everybody in the team is aware of what everybody else did. Corporate memory can be short. It can be truncated. Your documentation is the line of defense to ensure that all your great learnings, all your expertise continues to have impact on that project long after you left. It's part of your professional responsibility to defend what you did. And it's a great opportunity to add greater value. Now, every time I show a workflow here, I'm showing it just linear. Very simple, linear workflows. It's not very complicated. It's very practical to represent a workflow as a linear workflow. But don't get me wrong. I understand that, of course, workflows in best practice should not really be linear. In fact, as we mentioned previously, with the concept of top-down modeling, specifically, we talked about the idea that we're learning as we work, and that this is adjusting, that we're ready to cycle back. We're very agile, we're very flexible, we are willing to learn new information and to adjust our course. And so we learn new things from every step. We're learning while modeling, and we may refine, modify the workflow due to new information. This may cause us to, in fact, cycle back, to branch, to skip ahead, to redo the current step over and over again. And so let me give you a couple examples of loops and branches that we would see on this workflow. Well, you load the data. When you start to get into data cleaning, you might recognize that there's issues with the fundamental data. You might have to go back to how the data was collected. You might need to get new data, in fact, or integrate new data. Declustering. When you visualize and check the results, you might see that it's not a good result. There's a fundamental issue. You did not do a good job correcting for spatial bias. And you'll go back and correct the way that you declustered. Maybe when you visualize the data, declustered, QC'd, the data is great. But you recognize that you really do need to model with multiple faces. You need to break it up, or multiple regions. You may need to have a whole new branch here before you can get to even close to making a decision. You might find that declustering was not enough, that you can now suspect based on secondary information that you're in fact missing some of the data and you need to do something more substantial. You need to get into a spatial debiasing approaches. There's so many different branches that may occur. We are learning while we are modeling. We're learning while we are stepping along in this workflow. Uncertainty. There's uncertainty everywhere. Data, statistical summaries, the models, everything we work with is uncertainty. Uncertainty, we might as well make it our friend because we're working with the subsurface. It's sparse, it's heterogeneous, it's uncertain. Sparse sampling, heterogeneity equals uncertainty. So there's significant sources of uncertainty on everything we're doing. And in fact, it makes a lot of sense that as we're building a workflow, we should be quantifying and considering the multiple sources of uncertainty. We load the data up, we start to do summary statistics of the data, and we start to realize that we don't actually know the mean of porosity over the volume of interest. There's a P10 and P50, P90 for the porosity mean and variance. Distribution could be different. Maybe when we're working with missing values, well, we try to impute missing data, and now we have missing data represented as a random variable. We'll talk about random variables later, but it is a value that can have multiple outcomes. Maybe we find out that the hyperparameters for declustering are uncertain, and we want to treat them as uncertain as part of the uncertainty model. We should be documenting all of these sources of uncertainty as we're building the workflow and as we're conducting the work. We will talk later about a variety of different methods for quantifying uncertainty that we will include. In the course, we will focus on getting a pretty straightforward workflow together. And then as we get nearer to the end of the course, we'll talk about quantitative methods to get uncertainty in, and we'll talk about revising the workflow to be able to account for all of those possible sources of uncertainty. The fundamental method will be through scenarios. When we have a change in the decisions, the modeling decisions or the modeling inputs, the statistics, this is a scenario. When we hold the modeling decisions constant and we just change the random number seed to capture spatial uncertainty, that's a realization. Now, the most fundamental part of building a workflow is loading the data. And I thought it made sense at this point is I will talk about loading the data so that you in the course can get the data loaded, get started with some data cleaning. And so to do that, what I'll do is I will talk about loading tabular data and gridded data, and I will go through a workflow that's available online in GitHub, which demonstrates various different operations or steps of working with this type of data that you could use for data cleaning. That should get everybody in the class started with working in Python as far as those types of steps within the workflows. Now, as we go along in the course, we will get into different steps. We'll talk about statistical summaries, and when we do that, we will cover in Python how to do that. For R, I have a lot of good documentation too that's available if anyone chooses to try to do this in R. So if you look at just basically a data table, and you look at what the raw data will be like for this course for a data table, and it's pretty standard, is it will be in a comma delimited file, a CSV file. If you look at the raw file, what you'll find is that the top row, there's comma, X, Y, facies, porosity, permeability, AI. That's the column titles. That's the name of each one of the variables in the data table. And then what you'll find is that there's numbers separated by commas. Every time you have a comma, that means that's a new column. And so if you put this together, you can actually take a comma delimited file and double click it if you have Excel installed on your computer, and Excel will read it directly in and load it in as a table. And so if you take this file and you load it in Excel, this is exactly what you get. You'll see that the first column has no name. It in fact is just an index. X, Y, locations in space, facies 1 and 0, shale and sand, porosity, values roughly between about 0.05 to about 0.3, permeability, probably up to about 1 Darcy, I think is the maximum or so, and acoustic impedance values that are shown right here. And so this is the well data file. Now, once again, we are working in 2D for this just to simplify all the issues around visualization, presentations, and so forth. And so everything's just X and Y right here. How do you load that in? How do you get that into Python? Well, it's pretty straightforward. Here's an example right here of a very simple code in Python to load it in. Now, whenever you write code in Python, you want to start by importing the packages that you want to work with. Some things are built in, basic mathematical operations and so forth, but many things you'll have to load a package. The good thing about the packages we use in this course is that they will generally be part of the standard Anaconda install, so you won't even have to install them. If we do run into packages, I think later on we may, where you have to do an install, I'll show you how to do that. It won't be a big deal. So NumPy, very well-known package in Python for working with gridded data, for running different mathematical operations and so forth. Pandas is the package associated with data frames, which allows us to load tabular data. Next, we'll set our working directory. This is not a big deal. We're just telling it where to look. Now, you could skip this step and provide full addresses every time you do anything with reading and writing. I like to do it like this. It keeps my commands nice and short and clean, easy to read. This is the step right here. This is where we're going to load in a data frame, which once again is the Pandas data structure for working with tabular data. We'll just give the name of the file, and so this example that I show and this data file is in fact available on my GitHub under my geodata repository. And in fact, this example sheet is available too. Here's the link to it right here. And so you can go ahead and just read this comma delimited file, give its name, and it will create a df object. The df object is simply a data frame. You could call it anything you wanted to. And so you could go ahead and use the print command. The df.iloc, iloc allows you to reference to sets or ranges of cells within that table. And so by doing it like this, what I'm saying is show me the first 0 is the first one, the column the row, I should say, with all of the names of the columns, of the variable names, up to 5. So I believe this will do from 0 to 4 of the rows, so 0 through 4, and also includes the names up here up top. And the colon here says, give me all the columns. And so, but you're effectively slicing that data frame to get a preview of the first couple of rows. Now, the df head command is a very convenient built-in function to data frames that basically does the same thing, and this is the output shown right here, where you can see the first 4 entries in the data table. And so we do that, and the reason we do that is so you can have a quick preview. This example, I believe there's about 200 or maybe 100 and something rows, and so you could just look at the whole thing. What would you do if you had a data frame with 10,000 rows, 100,000 rows, and you tried to visualize it? It's much more efficient to use the head command and just simply get a preview to just make sure that the data table looks okay. As I mentioned at the beginning, I will have a separate video where I will go through this workflow right here. In Jupyter Notebook, I have a set of code for some of the basics of working with data tables with pandas and data frames. So it should be pretty useful, where I go over how to load, how to do summary statistics and data checking, data manipulation and formatting, extracting subsets of the data, transformations of the data, and then reading and writing back and forth and just showing that. So I hope that this will be useful. I'll record it as a separate video. Now let's talk about gridded data. The gridded data in this course will be the two-dimensional seismic information, the acoustic impedance. You have it assigned at the well locations, but you also have it as a full grid. It's the only information you have in between the wells. It is available to you over the entire grid, 1 kilometer by 1 kilometer, but it is sampled at 10-meter intervals. So you'll have 100 by 100 mesh every 10 meters of acoustic impedance. It's stored as a comma delimited file, 100 columns, 100 rows with commas in between each one of the values. If you double click it, it will load into Excel like this. In fact, if you load into Excel and you just use the Excel conditional formats, you can actually very quickly visualize the changes and heterogeneity within that acoustic impedance field. So now how do you load that comma delimited two-dimensional matrix into your Python workflow? Very straightforward. A single command right here where we can tell it load text, put the name of the file, which is that CSV file. We just have to indicate what is the delimiter. It's comma delimited, so we just put a comma in the parentheses, and we're able to load it. This function is using NumPy, NP. When I declared NumPy or imported NumPy, I said note it as NP. So by putting NP dot, I'm saying use a NumPy function, load text. And what it's creating right here is a two-dimensional ND array. So that's it. That's all I have to do. Now maybe you want to move backwards. You want to move in the other direction, in which case you would save text, NP, give the name of the file that you want to save it to, and the name of the two-dimensional array that you want to save, and the delimiter that you want to use. Now with GeoStats.py, I have provided programs like PixelPlot, which use the same conventions as in GeoSlide for plotting gridded data. And so you could use that command from GeoStats.py functions in order to visualize this gridded data at any point to be able to check it out and see what's going on. Now maybe the gridded data you're working with is not the two-dimensional matrix. Another way that gridded data could be represented is as a one-dimensional column where it's cycling. Basically it's going across, then to the next, and the next, and the result is you take the 2D and you're converting it to a one-dimensional array. So if you have a 100 by 100 matrix, it's going to become a 10,000 lines or rows with only one column. So In that case, you can use the numpy from file command to load that single column into an array. Once you've done that, so this is a one-dimensional ND array. If you check the shape of it, you'll see it's 10,000 by nothing. So it's just a 10,000 by 1 ND array. Now at any point you can reshape it. You can say, well, take that ND array, which was 10,000 by 1, reshape it to be 100 by 100. And this reshape command is really cool because it actually provides you with now a two-dimensional array to work with, an ND array to work with. A third methodology for loading is at times you may actually save the file in the GeoEAS format. That GeoEAS format has a specific header, it's ASCII, and it's a one-dimensional column. I have provided a variety of functions like this ND array to GSLive that's able to take a ND array in 2D or 1D and convert it to a GSLive file that can be read by a GSLive program. I've also have a methodology where you can go the other way. Given a GSLive ASCII file with the data in GeoEAS format, you're able to load that into an ND array. And that's what this command is right here. When you load it up, you just have to specify which column you want to work with, because there might be more than one column in the data set. The column 0 means the first column, the NX and NY, so it knows what to convert it into, what type of array is it. You could put NX 10,000, NY is 1, and you would just get one column. Or you could put NX is equal to NY equal to 100, and you get the 2D ND array out. It reads in the name of the property directly from the data file, so column name is the property name that you may want to work with, so that's read to you too. Now I do a little test right here to check the two arrays, and what I can see is that the one that I worked with originally, wrote out and read back in, is the same as the original array. And in fact, the writing and reading works. There's no error there, and you can plot and visualize that too. So these are a variety of different methods for loading and saving and working with gridded data, getting it into Python, and being able to work with it, being able to save it. Sometimes you want to save your model because maybe it took a long time to calculate, and the next time you pick up the workflow, you want to do something new, you want to close the workflow, open it again. It might be quicker to load the models up than to rerun the models every time. And so there's a variety of reasons why we want to save and load. First and foremost, you want to load the data in so you can get started with the modeling project, with data cleaning, and so forth. I have this available, which I will go through in another video, in which I will discuss various steps with regard to working with gridded data, data visualization, summary statistics data cleaning, other types of operations and transformations, how to make arrays or modify arrays, searching, manipulating, performing queries. That's pretty useful and powerful too. All right, so let's go ahead and just finish up right now. Let's get the big picture again. Remember, what we're doing is we're going to in general be building a reservoir modeling or subsurface modeling workflow based on the idea of data integration for reservoir modeling. We want to integrate all the available information together to build multiple scenarios and realizations to sample some uncertainty space, some possibilities of what's going on within the subsurface. We're going to apply to all of these models a transfer function that gets us to a decision criteria. We'll have a distribution of that decision criteria. In this case, the transfer function got us to a recovery factor. We have a recovery factor distribution based on the uncertainty model, and then we're now able to make a decision accounting for this uncertainty. All right, that's the end of lecture number 2 on the basics of building a workflow or workflow design. We talked about the basic building blocks, steps, how we could be looking at loading data, different types of operations, visualizations and checking and so forth. And we also talked about in a little bit more detail about data loading. We'll get more into data operations and so forth as I show you in the next videos the hands-on with regard to working with data frames and gridded data. We provide a lot more granularity and detail at this point just to get people in the class started with working with loading the data and doing basic QC and checks of the data. I think that's very useful. As we cover additional theory with regard to different types of operations, the working with subsurface modeling, we will provide a lot more details about how to do that in Python. Also, of course, I have quite a few examples, demonstrations available in R if anybody's working in R. And so I hope this is useful to you. Once again, I am Michael Perch. I'm a professor here at the University of Texas at Austin. I am the Geostats Guy on Twitter and also Geostat Guide lectures. Geostats Guide lectures are available on YouTube, and a lot of my materials are available on GitHub, such as the workflows that I have discussed here in this lecture. All right, I hope this was helpful. Okay, bye.